Afternoon, everybody. So great to see so many of you here on this wintry day. It feels really the spirit of Christmas with the white outside. Mr. Dean, Vice Deans, colleagues, students, great to see you here as well. It's my pleasure to be invited to give to you this talk here this afternoon. So the title is we're going to build stars, we're going to build planets, a little bit about the ingredients for possible life also elsewhere in the universe. And it's good to remember that Christmas 2020 and Christmas 2021, we were of course in isolation. And the one thing that was still possible in that time, we were not able to gather here like we're doing here today, but what was possible was to not just look down, but also look up at the sky. And on a beautiful evening, maybe tonight, you will see lots of stars there, maybe not the Milky Way, you need to go a little bit further away from the city lights. But the wonderful thing of this is that it was available to everyone, everywhere in the world, and it gave some comfort to people to just go there and stare even in isolation and just ponder these big questions as to where do we come from and what is our place in this gigantic universe. Now, one of my hobbies is actually astronomy and art. And as a Dutch person, I don't have to go very far, look very far. I can just go to Vincent van Gogh and look at one of his paintings here, the Starry Nights with the Big Dipper actually over the sun. But you can also go, across the entire world, and you see that, the night sky fascinates not just scientists. It really fascinates everyone, the general public. And you see that in art, you see that in poetry, you see the music. But to me, these kinds of paintings are really an enormous inspiration. And this is here the Milky Way dreaming, and Aboriginal in Australia, who of course have this beautiful southern sky above them. And what they have here is basically this Milky Way being part of their cosmology, the way also their society is organized. Through these dreamings. And what you see here is actually the seven sisters that are actually hidden here in the heart of the Milky Way, with Orion actually chasing them. Good. Well, we're talking about Christmas, about birth, and where were we born? Where was our solar system born? Well, what you see here is on the southern sky, you see the Magellan Cloud, you see here the Milky Way, you see the stars, but you also see all of this dust here in the Milky Way. And our solar system was born some 4.5 billion years ago in one of these very dark clouds. And that's sort of the nativity story that I will tell to you today. If we actually, rather than looking up at the Milky Way, if we were able to sort of go out of the Milky Way and be able to look down actually on it, then it would look something like this. This is an artist's impression, obviously, but it is based on actual astronomical data. And so here we have the heart of the Milky Way, where we now know there is a supermassive black hole. That was the Nobel Prize of 2020. And we see here these structures, the spiral arms in the galaxy. A galaxy is, of course, a collection of several hundreds of billions of stars. And our sun is just one of those stars. That is located here somewhere in the outskirts of the Milky Way. And so we live actually on this rather small rocky planet around a quite ordinary star in the outskirts of a galaxy. And of course there's not just one galaxy, there are several hundred billions of galaxies in the universe. So this makes this whole question already of, are we alone, puts it in a totally different perspective. Good. Well, people have, of course, speculated about the possibility of planets around other stars for centuries, dates many, many centuries. But the actual astronomical proof didn't come until 1995, which led to the Nobel Prize in 2019. And, for example, original discovery made here through the wobble that is actually induced by the unseen planet But then, since then, many planets being discovered through the so-called transit method, in which a planet goes in front of the parent star, and that then results in a tiny little dip in its intensity. And not so long ago, Venus went in front of the Sun, and that also resulted in a tiny little dip in the Sun's intensity. Good, so that discovery has, of course, led to many related fundamental questions. You know, where are those planets born? How are they formed? How unique is our solar system? And which of these planets could actually be habitable? And one thing that we've learned now from some 25 years of research on exoplanets is that there's an enormous zoo, actually, of those exoplanets. You have very small planets, like Earth. You have very big planets, giant planets, like Jupiter, like Saturn. And on average, we now know that every star has at least one planet. Some of them have more, maybe some of them somewhat less. But the bulk of those planets turn out to be of a type that we do not have in our own solar system. We call them super-Earth or mini-Neptune, somewhere between 1 and 10 times the mass of the Earth. And that's, raises then, of course, the question, why are so many of these planets of that type? And why don't we have them in our own solar system? So those are some of the questions that we now want to start to address. And now that we've found these planets, we also want to characterize them. What is their composition? Can they be habitable? And again, to put that in the context of our own solar system, how were we formed some 4.5 billion years ago? And we actually get very exciting data on that through various missions. Here going to an asteroid. The Japanese mission, the Hayabusa, has picked up a little bit of material from an asteroid. Also the NASA mission has done that, OSIRIS-REx, and they're bringing that to Earth. Can be studied in a laboratory on Earth, that material. And that tells us something about the early solar system, and in this case, rather close to our parent star, to the Sun. Then there was the fantastic Rosetta mission in 2014, for the first time that humanity has actually landed on the surface of a comet. Now, a comet is, of course, not just rock, it is a mix of rock and ice, and it was actually able to travel with this particular comet for some 2 years. And was able to sniff all the gases that actually came out of that comet. And I'll come back to some of that comparison between cometary and interstellar material. So let's actually start our journey to the story actually as to how stars and planets are formed. But first I want to pay tribute actually to all the young people with whom I've had the pleasure to work with, my wonderful group of PhD students, postdocs, colleagues all across the world that has made this research and this topic actually so much fun to work in. We've also been very fortunate that over the past 30 years, a number of facilities have come online that are particularly good for this field of astrochemistry or molecular astrophysics, because we do most of our observations in the infrared, where molecules can vibrate, and we do it in the millimeter part of the wavelength range, where molecules can actually rotate and have their emission lines there. And we have had a number of space missions, and especially the Herschel Space Observatory, ground-based telescopes like the ESO Very Large Telescope, ALMA, that I will come to in a moment, and then of course JWST, the Webb Telescope, that was launched last Christmas Day, and for which first data have started to come in July, and then the extremely large telescopes that sort of are the next step for ground-based astronomy, in the case of the European Extremely Large Telescope, less than 10 years away. So, also for the young people here in the audience, this is really an enormous opportunity. There will be fantastic instruments available if you want to study star and planet formation and exoplanet research in the coming decades. They are being built at this moment. All right, good. Well, if you look up at the night sky, you will likely see Orion, that you see over here. But few people actually ask the question, what is actually in between those stars? It's not empty. It's filled with a very, very, very dilute gas. The denser concentrations of that gas we actually call clouds. I think also a little bit of clouds in the Earth's atmosphere, but then a lot more tenuous. And you see here the Orion Nebula, that is here in the sword of Orion, that is a beautiful example of that. Now, these dark clouds are important because they are actually the regions in which we find molecules, but also that is where new stars and planets are being formed. So what you see here is actually the Carina Nebula. You see these dark clouds now against a bright background. That's why we can actually see them. And these clouds consist of both gas, and that gas is mostly hydrogen, but they also contain these tiny little dust particles, these tiny little particles that we call grains, that are about 1/10 of a micrometer in size. So think of sand particles that you also find on the beach, but then maybe a factor of 1,000 to 10,000 smaller, consisting of silicate material. Now, the density in these clouds is very low. It's of the order of, say, 10,000 particles per cubic centimeter. 1 cubic centimeter here in this room contains some 3 times 10 to the 19 particles, and even a good ultra-high vacuum in a laboratory on Earth still has some 100 million particles per cubic centimeter. So when an astronomer talks about a dense cloud, it is really, really much, much more tenuous than anything that you're used to in a laboratory on Earth. It's also very cold. It's only just above absolute zero. That's on the Kelvin scale. So in the Celsius scale, it's minus 263 degrees. So you see already under these conditions, where so tenuous, where one atom meets another atom maybe only once every 100,000 years or so, you would say, probably not much is going to happen. But as we will see, these clouds actually turn out to have a very rich chemistry. So if you look at sort of the periodic table that the astronomer has, it's slightly different from what you had in high school, or even the one that you see up here, in the sense that hydrogen is by far the most abundant element. If you put that at 1 by number, then helium is the next one at about 10%. But of course, helium doesn't do much chemically. The chemically more interested elements are carbon, nitrogen, and oxygen, the elements that we are made of. And those are down by several orders of magnitude at the level of of a fraction of a promille, actually, compared with hydrogen. So indeed, it took some convincing of astronomers to turn their receivers on these clouds like Orion and look for molecules, because the chemists were basically saying that they wouldn't find anything. So the surprise was that they actually turned out to have this very rich chemistry. So let's look a little bit about chemistry between the stars, and actually one of my favorite sources is here, this tiny little source in the snake carrier in Ophiuchus constellation. What you're looking at here is an image that is taken in the infrared, so somewhat longer wavelengths than we normally look at with our own eyes. And that's in the infrared is where we see all of these young stars. That's all of these red dots is where we see them. Now, what we do is we actually point our telescopes at these clouds, and then we can unravel the light into the various frequencies, the colors of the rainbow, so to say, in this case at millimeter wavelengths where the molecules have their rotational transitions. And thanks to the laws of quantum mechanics, actually every molecule has its own unique fingerprint. And that is how we can actually identify them. You can think of this as a barcode, just like you can scan a product in the supermarket. You can also scan it basically here and say, okay, all these lines here are due to this particular molecule. And it's a very unique and very accurate method. There's frequencies that are accurate to 1 part in 10 to the 7th. And often we have hundreds of lines of a molecule that uniquely characterize that molecule. So in this case, you see already dimethyl ether, you see several lines, you see methanol, you see methyl cyanide here, SO2, a whole zoo actually of molecules that we find them. But in total, more than 245 different types of molecules have already been found. Of this particular solar mass, young star that is being born at this moment in this cloud, we actually used the Atacama Large Millimeter Array, to which I come back in a moment, to do a chemical inventory, actually. And what ALMA allowed us to do was really do this chemical inventory of not just an entire cloud, but really zoom in on the places where individual stars, like our sun, are being born at this very moment. And we can actually now study the chemistry on the scale of a planetary system. And what we found is a huge number of lines. This is just a tiny part of the total spectral coverage that ALMA is able to do. But just in this relatively small frequency range, we already found more than 10,000 lines. And also we have an image of each of these 10,000 lines. So that already shows you the challenge and also the interest of many people actually working on these data. So here are just some of the molecules that we identified there. We went really for the sensitivity of ALMA from 2 carbon molecules to 3 carbon molecules. Also some interesting, what we would call prebiotic molecules that have, say, a C and O bond in here, that are sort of the beginnings of peptide-like bonds. Here you see another example, sort of precursors also of amino acids, acetamide that you see over here, although the simplest amino acid, glycine, we haven't found yet in this particular molecule. So here you see actually another molecule that is actually quite abundant in our interstellar clouds. That's of course ethanol. I think that Orion Cloud Nebula has something like 10 to the 27 bottles of whiskey in terms of equivalent amount of alcohol. So this is more to say that if you run dry during the bottle later on, then you can tap a little beer out of an interstellar cloud. Although, you know, in terms of percentage with respect to water, the alcohol is at the level of a few percent. So, indeed, thanks to ALMA, we are able to go from relatively simple molecules that we find in these clouds, like carbon monoxide, like water, like methanol. We go to more and more complex molecules, like you see here indicated. And I think there are quite a number of chemists actually in the audience that will be able to name all of these molecules. We also have even larger molecules like the polycyclic aromatic hydrocarbons, for which we see the infrared bands very clearly actually throughout the entire universe. These molecules are very sturdy against UV radiation, and they are present in quite large amount. Although in this case we can only identify these molecules as a class and not as individual species. The simplest amino acid, glycine, has not yet been identified, and this little molecule that may or may not be important for the origin of life, this is actually caffeine, has also not yet been identified in space. It's certainly important for the maintenance of life, so we'll leave it at that. But the point is, these molecules are not that much bigger than the ones that have already been identified. So we think that actually, that with pushing it further, we should be able to find them. Now, the molecules I talked about so far were all molecules that we saw in the gas phase, as a gas. Now, under the conditions in space, you have both gaseous forms and you have solid forms. The liquid form is not present because of too low pressures. But we definitely have the solid form, the ices. And in fact, the universe turns out to be full of ice because these tiny little dust grains, they act actually as a deep freeze on which atoms and molecules from the gas can freeze out. I think this morning, probably, your car shield, windshield, you know, there was water molecules from the atmosphere that froze out onto your windshield and formed a little icy layer there. The same is happening in space on our interstellar grains, that we make actually an icy layer there, and we can also, these grains can actually also serve as a catalyst, not a catalyst in the chemical sense, but more a catalyst in the sense of meet and greet, bringing atoms and molecules together and letting them meet and greet and form new molecules. So, for example, oxygen can be turned into water, carbon into CH4, nitrogen into ammonia. Carbon monoxide, quite abundant molecule in the gas, freezes out, and then with 4 hydrogens you actually get methanol. And that's a reaction that is well known. And then we also have some bubbles in interstellar space. The CO2 is definitely also present. So we see here that our alcohol is on the rocks, and also with some bubbles that we actually have there for our cocktail again later today. So we are fortunate in Leiden that we actually have integrated sort of our observations and modeling and laboratory experiments that are important, sort of the triangle that we use for astrochemistry in one building, even on one floor, and the Leiden laboratory for astrophysics, which is now under the direction of Harold Linnaert, has been very important in sort of supporting but also driving a lot of the research that we've done. And that has been a very good training ground also for a whole generation of laboratory astrochemists. Good, and through those laboratory experiments, both laboratory experiments and observations with Herschel, and also theoretical modeling, we now think that this is the way that most of the water in space is actually formed. So here we have a grain. Once a day a hydrogen atom arrives on the grain, it goes off, forms a molecular hydrogen, but it can also encounter an oxygen. There we see 2 oxygens makes molecular oxygen, and now we actually make hydrogen peroxide. Yeah, those are all intermediates that we have seen both in space and in the laboratory. And then we make 2 hydrogens, and now we speed forward. We go from a few days to we go to 10 to the 4, 10 to the 5 years, and this is how we make our little ice mantle on the surfaces of the grains. So this is actually how we think that the bulk of the water in space has been found, and as one of my colleagues actually put it, if you think about it, if most of the water was formed in the cloud before the cloud collapsed to form a solar system, that actually means that the water that we have is older than the sun itself. So think about that the next time that you actually drink a little bit of water. Now, these water molecules are some 4.5 billion years old. They have, of course, been sublimated and recondensed and sublimated, but the bond really is between the oxygen and the hydrogens date from that very early period. Good. So here we see this once more as to how we make that. And of course, these kind of reactions can happen not just with oxygen and hydrogen. This is also carbon monoxide with hydrogen that makes methanol, and that also triggers a whole set of more complex molecules that we can form in that way as well. Okay, so, with this sort of scenario, and then also with the observations, we can then actually see, well, how much water is actually available to build a planetary system? Because if you think about ingredients for life elsewhere, water is certainly one of the key ingredients. And thanks to the Herschel Space Observatory, which was actually very well suited for observing water in space, we were able to detect water here in a planet-forming disks. And from the strength of this signal, you can actually count how many water molecules there are in this system. And in this case, it turns out to be, we actually chose as a unit oceans, because that was easier to think of rather than 10 to the 49 molecules or something like that. But this is actually 6,000 oceans of ice that are available for building planets in this particular system. In other words, our solar system, our Earth needs about 3 oceans, a few oceans. There's plenty of water available, at least for this, to build planetary systems with a lot of water. Whether that also happens is a whole other question, because there are many other processes that play a role in that, but certainly bringing water during the formation of stars and planets, there's plenty available. Okay, yeah, this has not gone unnoticed, even with the Big Bang Theory, who had at that time also the water and even the ionized water that we detected up there on the whiteboard. Good, so to summarize this part, this was sort of the chemistry part. Now after that we'll switch to more to the physics part. Interstellar clouds clearly have a very rich chemistry in spite of their cold and tenuous conditions. Complex molecules are formed around most forming stars, and they are present throughout the entire Milky Way, and also in other galaxies, even out to the edge of the universe. And as we'll see, there's also a large similarity with comets. So the building blocks for prebiotic material are certainly widespread available. Okay, good. More to physics. We've seen these dark clouds. How is actually now a planetary system formed? Well, a cloud can be stable for maybe 10 million years, but eventually gravity actually wins. And if gravity wins, that means that the cloud actually starts to collapse under its own weight and forms a protostar at the center. But because the cloud has a tiny little bit of angular momentum, it just rotates a tiny little bit, that means that not all of the material can continue to fall in radially, but part of that will actually come in a rotating disk around the young star. And that is actually the location where planets can form. And so you see this here in this nice animation of a rotating disk of gas and dust, where we are now forming a planet here, and that planet actually carves a gap, and that's important. It attracts sort of the material and carves a gap in its orbit, and while it's very difficult often to see the young planet itself, what we can see is actually this cavity, this gap that is actually made here by the young planet. And of course, this is consistent with the solar nebula hypothesis, as was put forward by Swedenborg and Kant. That we actually come from this Ur-navel, that we come from this solar nebula, where all the planets actually rotate in the same plane in the same direction. Well, here, when ALMA opened its eyes, was one of the first pictures actually that showed this beautifully. People were expecting a rather smooth structure, but instead what we saw was this very structured emission here with holes in there that are actually the size of a planetary system. And I guess this slide doesn't do quite justice to this beautiful image here with all of these planet-forming disks, this gallery here of potential planet-forming disks that we actually now see with ALMA, indicative of ongoing planet formation in many of these disks. Actually, the next step is, well, are these molecules then also available near these planet-forming sites? We talked a little bit about water, but this is some recent work that we actually did on one of these very highly structured disks, where we detected not just carbon monoxide, but increasingly complex molecules, including also the largest molecule detected to date in a planet-forming disk, which is actually dimethyl ether. And this was actually an ESO press release that we had on the International Day of Women, because this was actually led by a master student and had only women authors, 6 female authors on this particular paper. So that was a nice result. Good. So, to get to the planet-forming disks, summarizing a lot of work that has going on in the last decade, that nearly all of these young disks are surrounded, nearly all of the young stars are surrounded by disks. The sizes are comparable with our own solar system. The mass is enough to form a planetary system. Not necessarily giant planets, but at least terrestrial planets, often enough. And that we now see all of these fascinating structures in these disks that point to planet formation in action. In other words, the ingredients for planet formation in addition to the ingredients for chemistry, are also quite common in the Milky Way. Good, so a few words about technology, because Faculteit of Wiskunde en Natuurwetenschappen also is, technology is key to all of this. And just to give you an impression of how far technology has come, if you think of the far infrared wavelength range where Herschel was operative, you know, in the 70s, 80s, we had just single pixel cameras and, you know, looks not much like a picture. And then came Herschel and then had these beautiful images that we got there showing these dust clouds that are actually glowing here in the far infrared. And so really, astronomy and technology go hand in hand. Most of our science is actually driven by new instrumentation. Now, why did we need ALMA? You need, of course, always to make a science case as to why you need ALMA. Well, we wanted to observe these planet-forming disks. But on the scale of this image of this cloud, these disks are actually tiny, 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 tiny. There it goes. You can hardly see it. So we really needed the sharpness of ALMA in order to zoom in onto these clouds. So indeed, as Christoffel already mentioned, I was fortunate to be part of the group of scientists that helped push ALMA and also helped to bring the different communities together from both North America, from Europe, and also East Asia, and together then put this wonderful array here in northern Chile. So this was actually the first worldwide collaboration in astronomy. It consists of some 66 antennas located on a high altitude site. And why did we go to Chile? Well, this is already, the New York Times said that this is truly high and dry over there to go there. Now, we've upgraded the transporter a little bit from what you see over there to a little bit more fancy transporter, but for the rest, the environment is still the same as you see on that New York Times picture. So ALMA is really a testimony to high-tech technology, not just in terms of the antennas, but also of the receivers, of the backends, and also logistically, just simply bringing all of these components from all over the world together here in this very hostile environment in terms of dry and high that you see there. This is where all the telescopes were put together and tested. That's sort of at the mid-level where you can still think, say around 2,500 meters, and then put on a transporter to be put into the array at the high side. So this is sort of how that looks today, and it is still, whenever you are there at 5,000 meters, both literally and figuratively, a breathtaking experience to be there. It's one of the most beautiful places on Earth that I know of. Good, and here you see actually ALMA at night, that all the antennas actually follow one particular object on the sky. And then, of course, the supercomputer correlator actually then puts all of the signals from these telescopes, 66 telescopes, together in order to make a synthesized image that we can then analyze. Good, so ALMA, fantastic, but then, actually, since last year, we have Webb. And this was a very emotional moment on Christmas Day last year. When it was Webb launched, and there you see, you know, the last stage when Webb was released, and it's really bye-bye Webb, and there, you know, the solar array that came out. It was a very emotional moment that was almost exactly a year ago. Now, we had indeed been looking forward to this for a long time because of the instruments that are on board. The MIRI instrument that is actually built to a large degree by Europe, and also the NIRSPEC instrument that is also built partly by Europe. So I'm going to spend a little bit of time talking actually about Webb, because I assume that many people here are actually interested in Webb. Well, actually my own involvement and also the Netherlands involvement and also the Belgium involvement in Webb started more than 25 years ago. When we had to actually convince ESA and NASA that we needed the mid-infrared instrument. That was not at all obvious from the beginning. And then once we had convinced them and it was approved, then we had to build the instrument. And here you see some of the people in the Netherlands building actually the spectrometer part of MIRI. Now MIRI was also with Belgium. Belgium was a very important partner of MIRI, both in Liège and here in Leuven, with Christoffel and also Bart van der Bussen, who is here in the audience. Both in terms of making important components there of the control electronics, but also in the whole testing and planning of the mission. So it's wonderful, and I really treasure also all the collaborations that we've had on previous missions, but now also here on MIRI. So certainly the links with Leuven are very strong. Good. So we built the spectrometer, main optics, and basically the whole hardware of the instrument. We built that in Europe, tested and integrated it in the UK. Then it went for delivery to the US, to NASA, and there it was integrated together with the other instruments into the instrument package. And then it sat there actually for a number of years, waiting for the telescope to catch up. So remember, we built most of our hardware already between 2002 and 2008. That then sat there for quite a while the telescope, here you see the golden eye, was actually being built and tested. Here you see just to give you an impression of the 10,000s of engineers that actually made Webb happen. Then integrating it, then from Goddard it went to Houston. You may remember Houston, we have a problem, Houston. That is from the test chamber of the Apollo missions. And they were still there, and they were just of the right size to test and the full end-to-end test of Webb, and also a cryogenic chamber, and that was actually a wonderful way in order to do that. Now from Houston we went actually to Los Angeles, and there the famous sun shield had to be a test. That was a big development in order to make a sun shield that could keep Webb actually cold, and making it also such that it could actually unfold in space. Then from Houston it went actually to Los Angeles. From Los Angeles it went actually to Kourou on a boat. We don't know exactly which boat, because we didn't want the pirates to know that there was $1 billion telescope on that boat that could be hijacked. But it arrived safely and is here going into the harbor of French Guiana. And then, of course, it all had to be folded into this nose of the Ariane 5 rocket, the largest nose of a rocket that was available at the time, about 4 meters in diameter, so the telescope had to be folded, and also the sun shield, of course, had to be folded. And that was sort of the critical technology of being folded and then unfolding in space. Well, all of that went fine. It went actually remarkable fine, and that after the launch also there was an enormous interest of the press. I assume the same happened here actually in Belgium and all over Europe, but it was basically non-stop request for interviews and also demonstrations. We actually bought a 1 in 10 scale model that does the unfolding of the telescope and the sun shield exactly as it happened in space, and that has turned out to be extremely popular to take around Leiden and surroundings and then show to many different audience. And we also invested in Lego. Well, I'm looking here at the Vice Dean for Outreach and Education as inspiration, how much little Lego models can really help when you go to hospitals and to schools and children. And they really love it to build their own little Lego Webb model there. Good. Where is Webb now? Well, Webb is 1.5 million kilometers from Earth. 4 times the distance of the moon. It's at the so-called Lagrangian point, where the sunshade, where it's this very stable point, gravity from the sun and the earth actually balance each other, and so you have a very stable point, and also a point where you can always have the sort of the noise factors, namely the sun, the earth, and the moon on the same side, and that sunshade then in that direction. So actually Webb travels with the earth in its orbit. And so we had to do one more step, and that was, to me, actually one of the most anxious steps. That was turning on the cooler, because we could have a wonderful telescope and a wonderful instrument, but if it didn't go cold, we had to turn on an extra refrigerator. If it wasn't cold, we would just see noise. But fortunately in April that was turned on, and then we could take the first images, and you saw immediately the enormous improvement in the quality of the images compared with what we had previously. So big thanks to Miri, team, to everybody here also that worked on the instrument. Fantastic, the kind of data that we have now. Well, what makes Webb so unique? Well, it makes it unique that it's big, 6.5 meters. Here you see sort of a 1-to-1 scale model. You see how big it is. It's also unique because it has this unique eyes in the infrared part of the spectrum. So this is, of course, what we see. We were looking with Alma and Herschel in the radio part, in the microwave part. Webb is actually here in the infrared, the mid-infrared part of the spectrum. And the reason for that is twofold. For one is that one of the main science goals of Webb is to go very deep in the universe, to see sort of the first galaxies, the first stars in the universe. But the light from those first galaxies and stars is actually shifted in wavelengths to the red. And that is why you need to go to longer wavelengths than, for example, Hubble was able to see. The other reason is closer to my science, that we want to penetrate these dusty clouds and see actually what is in them. And again, if we want to be able to look through the dust, then we have to go to the longer wavelengths. You see here in the visible, we don't see much, but the moment we go to the infrared, you start to see all of these stars happening there. So, some of the first images of Webb, you've seen them already. Beautiful galaxies. This is a nice image here taken both in the near infrared and the mid infrared, and everything that is red is basically where star formation is happening at this very moment. And here is another beautiful one, the Cartwright galaxy, a cartwheel galaxy, where you see sort of 2 interacting galaxies, and you see here the spokes, where again a lot of formation of stars formation is happening at this very moment. This one was released just around Halloween, for obvious reasons. It's a little bit spooky image of the pillars of creation of that were of course famous from the Hubble Space Telescope. Here is the Miri view of this, but what I really like is that we now see very clearly those stars that are forming here, sort of, you know, at the tip of the fingers. That we see here. We see all of these young stars now forming there very clearly with Miri. And then this beautiful image that you've undoubtedly seen in the picture of a cloud that's irradiated by very massive stars. You see this very sharp rim here of the cloud, and inside this cloud is where again, all of the red dots are new stars that are being born there. You can already zoom in here, and you see here a young star with sort of its outflow, trying to clear its surroundings. They're being born. And here's another one. So the young star itself is somewhere over here, and here's the jet that is coming out of that young star, and it's plowing into the cloud, and you see it here in a bow shock. We also sometimes see structures like this one over here that we have no clue yet what it is. And that's, of course, the fun of these new telescopes. You know, you get to see things that you don't expect. And, you know, we're going to answer questions that we don't even know what the questions are. That's, so that is the fun, really, of these new facilities. Okay, in the last 10 minutes then, let's go back to planetary systems. This is a famous painting that is actually in our collection of a planetary system. It dates already from 1798, where they were actually thinking that, well, not all planetary systems do need to look the same. You know, this is our solar system at that time, 7 planets were known. But, you know, look at all these other systems. They were speculating already about it. Some of them have less planets, some of them have more, some closer to the parent star, some further away. Some have, you know, lots of comets in there, others not. Very interesting what they were speculating already at that time, universal solar system. Well, we now know that sort of the origin of that diversity, well, you know, what leads to that diversity, is probably happening in these planet-forming disks. That's where the planets are being built, where you get sort of these, where you make these planets. So you see here, indeed, how these tiny little dust grains actually collide with each other and forming larger and larger bodies. Sometimes when they collide, they also, you know, fall apart again, but overall, bit by bit, you start to build larger planetary systems. And so if you think of sort of planet formation 101, what would be a lecture B? Well, you start with these very tiny dust grains. We ultimately want to make, say, an Earth-like planet, but in between are some critical steps. And one of those critical steps is making planetesimals, sort of kilometer-sized bodies, exactly the size of comets, after which sort of gravity between these objects starts to take over and play a role in the dynamics, and leads then to sort of lunar to Mars type bodies, and then ultimately to something that may or may not look like our own Earth. So these comets are very important as the building blocks of planets. And we can sniff actually their content. We can do it through remote sensing, but the Rosetta mission has been fantastic in looking in detail at this particular comet. And the composition of that comet actually turns out to be very similar to what we see in our young disks, what we see with ALMA, and what we are now starting to see also with JWST. So Rosetta actually had a very good nose. In the form of a mass spectrometer that was on board, and that basically sniffed all these gases that were coming out of this comet, and seeing very much some of the same molecules that we also saw in our interstellar clouds. And even some of the complex ones. This is the nice zoo that we have of the various molecules that were found in this particular comet. You know, some of the smelly ones that you see over there, some of the, here some more smelly ones, but some of the noble gases that you have over here, some of the alcohols that you have there, but also, you know, glycine was actually discovered. The lion king, so to say, was actually discovered in this object. So, where do we go now from here? ALMA is giving us fantastic insight into these planet-forming disks. JWST is just coming online. JWST is mid-infrared, warmer. That's the inner part of the disk. ALMA is more the outer part of the disk. JWST, vibrational transitions, both gas, but also vibrational transitions in ices. That's what we're going to be able to do. That's the sort of the complementarity that JWST now brings to sort of studying the complexity of these chemical complexities of these sources. So if you look back at this cartoon, we were making sort of a planet-forming disk. We saw all of our molecules there, and they will be transported, either altered or unaltered, into the disk, and out of that disk, planets will form. So if I think of a planet sort of as a Christmas pudding, something that you may be thinking of these days, then what we are actually looking at is trying to find is actually the ingredients that went into making that mature planet, such as the water, but also the sugars, the flour, whatever else goes into making that planet. And we want to see how those ingredients actually differ with location into the disk. So we do that with a number of programs, and I'm now going to show a few first results from our program. So this is a little bit more for the specialized audience, but it's at the special request of Christophe that he wanted to see some results. We have results from ISIS, but I'm actually going to show some results on planet-forming disks that we now have. This is actually still a simulation of what we thought we might actually see. This is from the Guaranteed Time program that is called MINDS, that's led by Thomas Henning. Here's, for example, an important molecule, carbon dioxide. And this is a paper that we just submitted, where we detect not just CO2 itself in these disks. You see here this enormous forest of lines. We've never seen that before in a disk. And we can actually now have also the confidence that this is not noise, that you might at first think this is noise, but it's not noise. You can assign every line to either CO2, to HCN, to acetylene, and to even to 13CO2. That is clearly this feature over here. And we find that in this particular disk, there's much more CO2 than we had thought before, orders of magnitude more than we had thought before, leading to a very different CO2 over water ratio. Another recent surprise, benzene in a disk around a young star. This three set of lines is clearly matching up exactly with benzene. And here next to CO2 and another species that may be HC3N. In fact, this particular source, a paper that we are finalizing actually as I'm speaking, is a particularly interesting source. It's a very low mass star, something, only 1/10 or 2/10 of the mass of the sun. But it has this very rich spectrum with two weird bumps here that we can now assign to acetylene. This particular disk is full of acetylene. We've never seen it before. We even see the 13 version of acetylene there. And we see again benzene, CO2, even C4H2, we see those all present in there. Here you see sort of the match again between models and the data, and certainly at this early stage of the mission, this is an exceptional agreement already between our simulations and the models. So this enormous amount of acetylene, of course, points to a very high carbon over oxygen ratio in the gas, which is interesting if you want to make planets. I mean, what kind of planets are you going to make? Are you make very carbon-rich planets, or are you going to make very oxygen, water-rich planets? Our planet, the Earth, is extremely poor in carbon. It's down by 3 orders of magnitude compared with what you would expect. What will the planets be in this disk? What kind of planets are you going to make? We don't know yet, but at least the JWST is showing us a little bit of the diversity that we're likely going to find in there, and also the role that some of these dust traps, some of these that we saw in the ALMA images, may actually play a role in preventing some of the planets from migrating, but also locking up, say, water in the outer disk and preventing it from entering the inner disk. And this is another final example then of the only planet-forming disk that we know. PDS-70 has 2 confirmed young planets here in this disk. Crystalline silicates, something that ISO found and that Christoffel made fundamental discoveries in with forsterite here, the minerals, geology we're now going to. But now look here, this tiny little part here. Now we zoom this in. Water. That's where we see a lot of water present there. Well, maybe not a lot, but at least some water there. So it shows us that the inner disk is not completely drained of oxygen and not completely depleted by the fact that we have these 2 planets putting up a big barrier for anything coming from the outer disk into the inner disk. So this is just to give you a flavor that we are making a first peek into JWST. We're finding lots of interesting molecules already there that we hadn't seen before. That you see over here, and there's likely going to be much more that we're going to see. So will this actually get onto the new worlds? Here you see our planets in our solar system: Earth, Mars, Venus. Of course, only Earth's rich spectrum is not just CO2, but also water, ozone. Does that make a habitable world? What makes a habitable world? We don't know yet, but it's clear that we need to have these kind of spectra to decide between that. And this is, again, the improvement that Webb brings us. Hubble was able to see only this part of the spectrum, and now with Webb we see sort of these complete fingerprints, actually, of molecules in the atmospheres of giant, not just giant planets, but also Earth planets and super-Earth planets. So a much larger sensitivity and coverage. And some of the targets that are being observed already are not just giant planets, but also these fascinating Earth-like planets, like this TRAPPIST system, of course very well known here in Belgium, from Michel Guillon. I think there are some data already on this planet. I saw some data on this planet earlier this week. We don't know yet what we're going to see, but it's certainly a very interesting time to be studying these objects and searching for water or other signs that could be signatures of possible life there. Good. What has Webb seen? Well, it has seen some water already on one exoplanet. It has seen CO2 on another. And in fact, just, 10 days ago, this beautiful spectrum was published, involving also Lane here in this effort, showing here the beautiful carbon dioxide, very clear, water, very clear. Perhaps some other interesting molecules, such as sulfur dioxide. We don't know yet, but it's clear that Webb will have the capability of studying in this more detail. And you can also look at clouds. Maybe, after a few years of JWST, we will learn about the weather on one of these exoplanets. Clouds that form during the nighttime and go away again in the daytime. Some of these things are certainly also being studied with Webb. Okay, I want to end here and go back again to Christmas. It's a Christmas lecture, Christmas 1968, this beautiful image of Earthrise. Then Valentine's Day in 1990, where you have this tiny little dot there, the pale blue dot. That's when Carl Sagan asked the Voyager mission to turn around one more time and look back at Earth. That's our little home there. To me, astronomy is not just about exciting science. It's super exciting science. I'm a chemist by training, but I must say that having the universe as your laboratory brings in a totally different perspective. So I hope also that this science and astronomy brings excitement, brings inspiration. It also brings perspective. Where are we, this tiny little pale dot in the universe? It also brings in a sense of vulnerability, a bit of modesty, and also certainly tolerance. And I think that's exactly what we need in these days. We need to take well care of our planet, and we need to also remember that ultimately we are all together here and world citizens under this beautiful starry night. Thank you very much.
Thank you very much, and also for your very nice Christmas wishes. But before concluding here, I think, the program tells me that there is room for questions from the audience. Does someone want to address the question?
All the way up there.
Yeah, I can speak loud, so you can hear me from here.
Yeah. Yeah, that is a very good question. I think our planet itself, even though humanity is not taking well care of it. It is at least sturdy enough that it will survive for at least hopefully a few more billion years, even without us being present on there. But of course, the search for life elsewhere in the universe is ongoing through various programs. The difficulty is always that even if we would find it, even would find signatures in remote planets there that are indicative of life on such a planet, we would not be able to travel there. Even communication would be extremely difficult, or even if not impossible, given the distance to those sources. So in that sense, it will be one way and not a real interaction.
Thank you, indeed fascinating. But the question, you say we see the formation of stars, but when were these stars formed? How long has this light been traveling to catch the telescope?
Well, I'm actually, we are looking mostly in our cosmic backyard, so out to the distance of Orion, which is only, say, 1,500 light years away, so it may have been traveling for a few thousand years. Of course, my colleagues in the high redshift universe are looking at sources and even at molecules that were formed, a few 100 million years after the Big Bang, so more than 13 billion years ago. So there, the light has been traveling, for billions of years. But all of our research, in order to get the best sensitivity and sharpness, is happening sort of in our cosmic backyard. Yeah.
Thank you. Thank you for a very interesting presentation. And I must say I'm not at all a specialist, but I was intrigued by your explanation on how ice forms on these dust specks. As I understood it, that means that the dust is also older than the water. So does that mean that the silicate is older than water, and where does that come from then?
That's a very good question. In fact, we have some experts here in the audience that could explain that much better. But we think actually that the cores of the silicate grains are made in the outflows of dying stars, so the previous generation of stars. Those are the conditions, high density, warm, where you can, and that is actually an outflowing and cooling, and that's where you can condense sort of these silicate cores. So they basically come from the previous generation of stars. Yeah. But yes, you're right, the silicate grains are older than the water.
Yeah. Can you have the microphone there?
He's coming.
Very nice lecture. Congratulations, for sure. In one of your slides, you mentioned that new technology is needed in the measuring instruments. What technology do you think about, or is it still something for years or decades?
Yeah, so every mission, you need to look 30 years in advance, because it takes 20 to 30 years to develop such a mission. So technology development is going on at this moment. For example, for the next generation of far infrared, sort of the successor of Herschel, that's where, in terms of detector technology, a lot is going on. If we think of sort of the next big mission after JWST, but what comes after Webb? That needs to be already on the drawing boards if it's going to fly around 2045. And for that, extreme contrast, so extreme adaptive optics that will be needed in order to image these Earth-like planets next to a mother star. So those are some of the technology developments that are ongoing at this moment. Yeah.
Thank you.
We should have done it by blocks. Yes.
So you mentioned the difficulty of chemistry under conditions where there's little energy and molecules are far apart. So are there in the system things like catalysts or conditions that favor, like adsorption to substrate that favor chemical reactions, or is this not necessary? Is it just time and then the big number game that takes care of the chemistry, and just wait long enough that any reaction will happen, even under very unfavorable conditions?
A bit of both. I mean, certainly not any reaction will happen, but we have a large cloud and a lot of molecules and time. We also have time on our side, so in that sense, chemical reactions can happen. But basically, when you think of these grains, it's not catalyst in the chemical sense, you know, in the chemical sense where you would have the servers, say the d orbitals of the silicates or the iron or whatever else, promoting the reaction. In that sense, the service is passive. It's really a place to bring atoms together for long enough time for them to react. So that's where the meet and greet actually comes from. So that's on the surface. In the gas phase, at low temperatures, in fact, that was already discovered more than a century ago. If you have reactions between ions and molecules, not between two neutrals, those are very slow at low temperatures. The reactions with molecular hydrogen will almost never happen at low temperatures. But if you have an ion and a molecule, then Mr. Langevin already told us in 1904 that that will happen just as quickly at 10 Kelvin as it does at 300 Kelvin. At a fairly large rate coefficient. So ion-driven, actually, and then those ions are created by cosmic rays that interact with the cloud. So as long as you have some ions that drive the chemistry, or maybe some UV that can help drive the chemistry, then a lot can happen in the gas phase. Yeah.
I see a question in the back, and Bart, yeah, okay.
Wanneer is de eerste ster geboren?
Wanneer is de eerste ster geboren? Dat is een goede vraag. Dat is een goede vraag. Ik hoop dat Web ons daar het antwoord op gaat geven. Dat is precies wat Web ons probeert te vertellen, van wanneer de eerste ster in het universum is geboren. Dat weten we nog niet. Misschien maar 100 miljoen jaar na de oerknal. Een hele lange tijd geleden. Ja. Goeie vraag.
My feeling is that we must stop with this question. It is such a nice one. Thank you very much for asking it. And well, Ewine, thank you very much for this, I think, wonderful talk. I express the opinion of the whole audience by telling that.